Sauce here. This is a video lesson on using sigma notation for area under the curve estimates. This is going to get intense, but it's worth it. Let's consider the notation which poses the project. The area under the function 2 to the x on the interval from 2 to 4. And in this case, we're also going to be given n, the number of rectangles that we're going to use, equal to 5. We'll need to use 5 rectangles and the rectangle method for estimating or approximating the area under the curve. In general, 2 to the x is the function that we're going to find the area under and above the x-axis. And in general, the interval that's given has a lower bound that we could call A and an upper bound that often we call B. To help us understand what's involved in this project, I'm going to make a table to organize information, and we're also going to produce a graph. I'm going to choose 2 boxes to represent 1 unit and put tick marks at the lower bound and upper bound 2 and 4. I'm going to choose 1 box to represent 2 units on my vertical axis. So we have 4, 8, 12, and 16. In my table, I'm going to list important values in the domain, which are x values. And I could begin by choosing a value, which is the lower bound 2, and finding the value of the function at 2, which is 2 squared, or 4, which helps me plot that point. If I put 4 into my function, the value of 2 to the 4th is 16, which allows me to plot that point. Now I know my function is exponential, so if I've got these 2 points, I can sketch an exponential curve that passes through them to approximate my graph of f. Now the area under the curve means the area between this function and the x-axis. From 2 to 4 means I can put boundary lines at 2 and 4 and think of the area of this shape, which cannot be found geometrically because the f function curves. Now, if I'm going to use rectangles to estimate this area, then it's best to have every rectangle be in equal width, so they're all the same in width. If I'm going to use 5 rectangles, then I have to divide up my interval from 2 to 4 into 5 equal partitions. I can find the measure of each partition, and I call that delta x. In general, by calculating the width of the interval, or in general, b minus a, and then dividing by the number of rectangles that I wish to make, or n. Now in this problem, delta x is going to be equal to 4 minus 2 divided by 5, which is 2/5 or 0.4. Dividing the axis into 5 partitions looks like this. And those locations, those values of x, are important because it's going to be at those places and only those places that I find the sides of my rectangles. And I can represent the values at those places as vertical lines. Now, because these locations are so important, they're important because it's going to be those values of the function that I'm going to use as sides of rectangles. And I'm going to make my estimate by finding the areas of rectangles and adding them together. Those places in the domain are special enough that I'm going to make a list. I'm going to make a list of integers and start the first important location at 0 and call that location x sub 0. The next one would be x sub 1, then x sub 2, x sub 3, x sub 4, and I get to my last important location and call it x sub 5, and 5 equals the number of rectangles that I'm using. In my table, I'm going to list those important locations as k values. The k value that I start with is 0. And I go up by integers until I get to the last 5. So my k values in this problem start at 0 and go up to 5. Each k value pertains to a specific domain value x. So I could more precisely label this column x sub k. So x sub 0 is 2. What's x sub 1? The value on the horizontal axis that corresponds to a k value of 1, or we could say x sub 1 is going to be 1 delta x over from this 2. So the next value in my table that's important at a k value of 1 is 2.4. At a k value of 2, it corresponds to x sub 2, and the value on the axis at this location is 2 delta x's over from the beginning, or 1 more delta x from the last one that I found, which is 2.8. And I could go and finish the x sub k values by adding delta x's until I get to the last one. Why did I do that? Because I'm organizing the information that I need to produce rectangle areas that I'm going to sum together. And I'm going to use sigma notation to help me make that sum. Sigma notation requires integers. We can't use sigma notation with an index that has fractions in it. So I've had to take the step to translate or correspond my list of important domain values and associate them with integers so that in a final step I can create the sigma notation. That's where I'm going. I still have some more to do to get there. So these x values are going to become sides of rectangles. And we can visually see that if we draw the tops of the rectangles. So if I take this first line, which is the value of the function at 2, I can make it be the height of a rectangle by drawing the top right at that point on the function. And the height at 2 is determined on the left side of the rectangle, in this case with this choice. The second rectangle that I can make draws the top using the function value at x sub 1, which is 2.4. And again, by making the top there, the height is determined on the left side of the rectangle. So what I'm doing is I'm drawing tops to create rectangles, and all of these rectangles will have their heights determined by values of the function that are on the left side. this will produce the left side rectangle approximation. There's a right side rectangle approximation, but that would have me draw heights at points that made the height of the rectangle be located on the right side of the rectangle. And that would change my presentation. I'm going to stick with these 5 left-sided rectangles. The next thing in my table that I want to show is the heights of those rectangles. In general, I could call that F when I put x sub k into it. If I put the first k value of 0, which is an x value of 2, into my function, then I get 2 squared, and that's 4. That produced the height of 4 here, which is the left side of the first rectangle. I get the area by multiplying that height by the base. The base of this rectangle is delta x. We've calculated that to be 0.4. In my table, I could list the bases of these rectangles as a column that I could call delta x. And delta x is 0.4 for every rectangle. The next thing I could do in my table is produce the actual areas of the rectangles. In general, what I'd be doing is I'd be multiplying the base, delta x, times the height of the rectangle, which is a value of the function, f at x sub k. And for this first rectangle that has a height of 4 and a base of 0.4, I multiply them and get 1.6, the area of that first rectangle. Now, I could go and complete this table and fill in all of the possible rectangle heights and all of their areas. And if I did, I would be adding the first 5 in this table that includes 6 rectangles, and I would add them together to produce the left rectangle estimate. This last rectangle is the rectangle that we would use as the last rectangle in a right rectangle estimate. That height would be the rectangle that used this function value on the right side. But if I'm producing a left rectangle estimate, I don't use the last one. I sum these up to produce my estimate. I'm not going to complete this table because I'm going to prepare that sum as a series of terms and see it in a slightly different way. So to begin my series, I would repeat what I did for the first. I would multiply the base of 0.4 times the function, the value of the function found at that first location 2. And this expression, 0.4 times 2 squared, is the base and height that produces that first area. I'm going to continue. The second rectangle is the same base of 0.4 times the value of the function found by putting 2.4 into the function, or 2 to the 2.4. The third rectangle is 0.4 times 2 to the 2.8. Fourth rectangle, 0.4 times 2 to the 3.2. Last rectangle in the left rectangle estimate is found as the base 0.4 times the height found as 2 to the 3.6. When I list the rectangle areas and their calculation like this, it's produced a series. I'm going to translate these numbers into the general notation that represents that. In general, what I did was this 0.4 came from delta x, and this 2 squared came from putting x sub 0 into my function. Again, the 0.4 is delta x, and the 2 squared came from putting x sub 0, which is a k value of 0, which is an x value of 2, into my function, 2 to the x. Continuing with this general representation, I have delta x times the value of the function, where I'm increasing the k value to 1. And then delta x times, I keep putting a parenthesis, leading parenthesis there that I don't want, the value of the function at a k value of 2, or f at x sub 2, plus delta x times f of x sub 3, and then the last rectangle is found as the product delta x times f at x sub 4. The last k value of 4, which corresponds to an x value of 3.6, put into the function. Now that we see it in general terms, we can think of this as a sigma, the expansion of a sigma algorithm. We can wrap this expansion up and express it in sigma notation. When we do, we use sigma to represent the sum. The argument is going to be the same structure every time. The argument always includes a delta x, which is the base of a rectangle. And we're also always multiplying by a height, which is a function of a k value. The only thing that changes in this expansion is the number 0, 1, 2, 3, which represents a k value. The index starts at a k value of 0 and goes up by integers until we get to the final k value of 4. So here we have, in general notation, in general terms, the sigma notation. And we're going to write this more specifically. The index is still 0 to 4. Delta x is 0.4. And we're going to multiply by the function. But here is something kind of tricky. We can't use f of x because this needs to be a function of integer values k. Sigma notation requires the index to be integers. So the function itself isn't a function of x, it's a function of k. In other words, I have to take the function of x and convert it to be a function of k. How's that done? What mathematical process takes k values and turns them into the appropriate x value that's needed to get the appropriate function value to correctly calculate the area? Well, that function is always a function where we change what we put into the function to be a, the same value that is the lower bound of our interval, plus delta x times k. In this way, we can use f of x, but rather than putting x into it, we put a plus delta x k being the variable, a and delta x being numbers that are known, and it converts it into the function of k. In this example, the function is 2 times the input, and the input is going to be a delta xk, or in the exponent, 2 plus 0.4k. Let's check it. Does this sigma notation produce the expansion that we know is going to produce the sum of these rectangles, which will estimate the area under the curve? Well, we start with the first index value of 0. So this will be 0.4 times 2 to the 2 plus 0.4 times 0. 0.4 times 0 is 0, so 2 plus 0 is 2, and we get the 0.4 times 2 squared that we expected. Let's check the next one. With a k value of 1, we get 0.4 times 2 to the 2 plus 0.4 times 1, or that's 2 to the 2 plus 0.4, which is 2 to the 2.4 that we expected. Let's jump to the upper bound of the index 4. If we put our final index value of 4 into our argument, it should produce the final part of my series. 0.4 times 2 to the 2 plus 0.4 times 4. 0.4 times 4 is 1.6. 1.6 plus 2 is 3.6, so that is 0.4 times 2 to the 3.6. This is the sigma notation which produces this series. And this series was the sum of the first 5 rectangles whose heights were determined on the left side. If I put this into a calculator or software that is capable of handling sigma notation, I would produce the estimate, and in this case that's been done, as 37.556. Why would we use sigma notation to produce estimates if it takes that much work? Because we can produce a better estimate by using more rectangles. If we used 20 rectangles, then the bases would be much thinner, but it would be more accurate because these spaces between the curve and the top of the rectangle would diminish. The error would diminish and our approximation would get closer to the exact area. But imagine calculating by using a table the area of 20 rectangles. It would be very tedious. So it would be better to use the patterns and put it into sigma notation and use software or other mathematical equations to find the sum. And we can go further than that. What if we wanted to use 1,000 rectangles? We wouldn't want to do it by hand. But if we establish the patterns and put it into a sigma notation, then we could use 1,000 rectangles, which would mean an index that was used 1,000 times, but the accuracy of that estimate would be very, very close to the actual area. And what calculus does, and all calculus is this process where we literally then use an infinite number of rectangles. And the approximation then becomes or goes towards or approaches the exact area under the curve when we approach using an infinite number of rectangles. This is the beginning of what we're going to call integral calculus.